All right, so we're up to lecture 20 already. Not much left. So there are two topics that I want to cover before the term ends. The first I just started, which is on eigenvalues, and the second has to do with inner products on vector spaces. So we have T from V to W is what we've been studying, a linear transformation from a vector space V to a vector space W. In the case when we let W equals V, it still is a linear transformation, but a linear transformation from a vector space to itself is also called a linear operator. So I'll use both terms interchangeably. A linear operator is just a linear map from V to V. And the object is somehow to understand this linear map. So we say a subspace W of V is invariant with respect to T if T of W is contained in W. So in general, if this is your vector space V and this is W, T of W can be anything. But if W has the property that any vector in W just gets mapped to something inside of W, that simplifies things a little bit. And knowing what invariant subspaces are helps us understand the operator. So there's sort of two trivial invariant subspaces, 0 and V itself, because T of 0 is 0 for every linear map, and T of V is certainly contained in V. Could be equal to V, but it's contained in V. So these are the sort of the trivial invariant subspaces, and we're interested in the non-trivial ones, if they exist. And the simplest non-trivial invariant subspace would be a one-dimensional subspace. It's not 0. So if the dimension is not 0, it's at least 1. The simplest non-trivial subspace would be of dimension 1. So W is just subspace spanned by one vector. And T of V has to be in W. But if W is one-dimensional and V is a generator, basis for the subspace, T of V is just some scalar multiple of V for some scalar lambda in the field. Could be the real numbers or the complex numbers. And a number V such that T of V, so V is one-dimensional, so V is a non-zero vector. This number lambda is called an eigenvalue, and V is called an eigenvector. So whenever there is a one-dimensional invariant subspace of some linear operator, there's a non-zero vector V and a number lambda, a scalar lambda, such that T of V equals lambda V, and lambda is an eigenvalue. I mean, geometrically, what this means is as follows. I mean, here's your vector space, and if your vector V is some non-zero vector pointing out of the origin, when you apply T of V, it just stretches it. If lambda is positive, if you're over the reals, or stretches it in the opposite direction, but it still is a vector on the line through the origin in the direction of V. So there's some line through the origin which is preserved by the linear operator T. So an eigenvector is just a vector that the linear operator T takes to some scalar multiple of itself. And what is called the spectrum of T is the set of all eigenvalues of T. So let's take a very simple example So let's just recall, if you have T from V to V, and if the dimension of V is n, and if the vector space V has an ordered basis, E1 up to En, then T has a matrix with respect to the ordered basis, called this E, which is some n by n matrix. Right? And we know how to calculate the matrix for a linear operator, called this A. So this is the A is the n by n matrix, which is the matrix for the linear operator T with respect to this basis. And T of a vector V is what? It take the matrix A, the coordinate vector for V with respect to the basis, and that gives us the coordinate vector of T of V with respect to the basis. Right? So this is the basic connection between a matrix and a linear operator. Once you specify a basis for your vector space, the linear operator has a matrix. And conversely, if you have any matrix A, n by n, you have a linear operator where you apply A to the column vector x1 up to xn, and you get, that's T of x. Right? So if I want to make things easy, I can just start with a matrix, a square matrix, and look at the corresponding linear operator. So for example, suppose A is the matrix 2, 0. So we have the linear operator T of xy is A applied to xy. So that's 2, 0, 0, 3 applied to xy. That's 2x, 3y. So T sends the vector xy to the vector 2x, 3y. And if you look at this for a second, you can see if you apply T to the vector 1, 0, that's A of 1, 0. When x is 1 and y is 0, this is 2, 0. 2, 0 is 2 times 1, 0. All right, now that's clear. 2 times 1 is 2. So if E1 is the vector 1, 0, T of E1 is 2E1. So for this matrix or this linear map, E1 is an eigenvector with eigenvalue 2. And T of 0, 1, that's the matrix A times 0, 1. When x is 0 and y is 1, this is 0, 3, which is 3 times 0, 1. So T of the vector E2, E2 is 0, 1, T of E2 is 3E2. So E2 is an eigenvector with eigenvalue 3. So if we're working over the field of real numbers, my vector space is just R2. And I have this map T from R2 to R2, or A from R2 to R2. So here's the vector E1, and E1 gets sent to 2E1. E1 is just stretched in the same direction. And E2 goes to 3E2. So if you want to understand this linear operator acting on the ordinary XY plane, it takes E1 and multiplies it by 2. It takes E2 and multiplies it by 3. So if you have any vector, this is V, the X coordinate is multiplied by 2. The Y coordinate is multiplied by 3. So V gets sent to this vector over here. It's not on a straight line, it's just my bad drawing, but the X coordinate is doubled. The Y coordinate is tripled. So for this extremely simple linear transformation, we find the eigenvectors and the eigenvalues. In fact, there's a basis of eigenvectors, and the standard basis is in fact the basis for eigenvectors. Okay, so this is maybe the world's simplest example of a linear map and its eigenvectors. Yeah, any questions about this? For a more interesting example, this is example 1, I think, in the notes. We have the matrix A, a 2 by 2 matrix, which is 7 minus 4, 5 minus 2. And we have the linear operator T of V equal to the matrix A times V. So that means if V is XY, this is 7 minus 4, 5 minus 2 applied to XY. We get the vector 7x plus 5y minus 4x minus 2y. So this is my linear operator. And I claim that I'm going to show, I show in the notes, that the set of eigenvalues, the spectrum of A, in this case is also 2, 3. This says there's an eigenvector with eigenvalue 2, and there's an eigenvector with eigenvalue 3. So suppose I let V1 be the vector minus 1 plus 1. So what is T of V1? That's A applied to minus 1, 1. So that's 7 minus 4, 5 minus 2 applied to 1 minus 1, 1. That's minus 7 plus 5 is minus 2. 6 minus 2, no, 4 minus 2 is 2. This is 2 times minus 1, 2. Right? Multiply this vector by 2, you get, minus 2, 2 times minus 1, 1. Multiply this vector by 2, you get minus 2, 2. This is 2v1. So T of v1 is 2v1. So v1 is an eigenvector with eigenvalue 2. If I take the vector 2, v2 is minus 5, 4. What is T of v2? So I take my matrix applied to the vector minus 5, 4. This is minus 35 plus 20 is minus 15. 20 minus 8 is 12. If I factor a 3 out of this, I get minus 5, 4, which is 3v2. So v2 is a non-zero vector, and T of v2 is 3v2. It's an eigenvector for the eigenvalue 3. So this linear operator has at least 2 eigenvalues, and for each of these eigenvalues, I found one eigenvector. Right? You might say, how did I find these vectors, the eigenvectors? Well, I'll show you in a moment, but in any case, these are eigenvectors, and that's really all I need to know. Right? Any questions about that? So the first theorem about eigenvalues is the following. I have a linear operator from V to V and over a field F. So V is over the field F, which can be the reals or the complexes. And let lambda be a scalar, an element of the field. So we define E of lambda. So this is the set of all vectors in the vector space such that T of V is lambda times V. And so I claim that E of lambda is always a subspace of V that is invariant with respect to the linear operator. And lambda is an eigenvalue of T if and only if E of lambda, which I will show is the kernel of the linear operator T minus lambda I, is not just the zero vector. So let me prove this. So I have T from V to V and E of lambda as all vectors V in the vector space where T of V is lambda times V. So of course, T of 0 is always the zero vector. And for any lambda, you take any scalar times the zero vector, it's still the zero vector. So 0 is an E of lambda for all lambda, right? Every one of these sets contains the zero vector. If V1 and V2 are an E of lambda, then T of V1 is lambda V1, T of V2 is lambda V2. So T of V1 plus V2, well, that's T of V1 plus T of V2. Of course, T is a linear operator, which is lambda V1 plus lambda V2, which is lambda times V1 plus V2. So V1 plus V2 is an E of lambda. So E of lambda is closed under vector addition. If V1 and V2 are an E of lambda, so is V1 plus V2. Also, if V is an E of lambda and C is any scalar, then T of C times V is C times T of V. That's C times lambda of V. But C times lambda is the same as lambda times C. So this is lambda times CV. So CV is also an E of lambda. So E of lambda contains 0. It's closed under vector addition and scalar multiplication. So E of lambda is a subspace. And if V is an E of lambda, then T of V, which is lambda V, is also an E of lambda because the subspace is closed under scalar multiplication. So E of lambda is T invariant. It's invariant with respect to T. And lambda is an eigenvalue with eigenvector V if and only if T of V is lambda times V, which is the same as saying T of V is lambda times the identity operator times V, which is the same as saying that 0 is T of V minus lambda I times V, which is exactly T minus lambda I, that operator applied to V, if and only if V therefore is in the kernel of T minus lambda I, which means the kernel of T minus lambda I contains a non-zero vector. It's not equal to 0. As a matter of terminology in linear algebra, what is called the geometric dimension of an eigenvalue lambda is the dimension of the eigenspace, the vector subspace, E of lambda. So lambda is an eigenvalue if and only if its geometric dimension is non-zero. There's at least one non-zero vector in the eigenspace. So the eigenspace has dimension at least one. Let's look at another interesting example. Suppose we have T from F2 to F2, two-dimensional space, determined by the matrix A equal to 0, 1, minus 1, 0. So let's say there are two cases. Either we take the real numbers in the real vector space, or the second case is we take the complex numbers. So let's start with T as a map from the reals. So A of 0, 1, minus 1, 0, that means the vector E1 gets sent over to here. And the vector E2 gets sent to minus 1, 0. In other words, T, or A, is rotation around the origin by pi over 2 radians. Right? If you go back and review, what is the matrix for a rotation in R2 by an angle theta around the origin? R theta is cosine theta, sine theta, minus sine theta, cosine theta. So if you take the rotation to be pi over 2, this is cosine pi over 2, sine of pi over 2, minus sine of pi over 2, cosine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So you get exactly this. So Geometrically, this corresponds to a rotation by 90 degrees or pi over 2 radians. So geometrically, no vector is stretched because every vector is rotated. So no eigenvalues or eigenvectors, except 0, of course. Sorry, not even 0. No, this is the empty set. So geometrically, if you're rotating vectors, nothing is being stretched in the same direction, so there can't be any eigenvectors. But we can also prove the same thing algebraically. So algebraically, I want to show A has no eigenvector. So suppose A times some vector xy, that's 0, 1, minus 1, 0 applied to xy. Suppose that's lambda times xy for some xy. Let's see, when I multiply the matrix times this, I get minus yx equals lambda x lambda y. So this says that x is equal to lambda y, and minus y is lambda x, which means y is minus lambda x. So x is lambda y, and y is minus lambda x. So x is equal to minus lambda squared x, which means lambda squared x plus x equals 0, or lambda squared plus 1 times x is 0. So x and lambda satisfy this equation, but in the reals, square is never equal to minus 1. Lambda squared 1 is greater than 0, so x has to equal 0. And if x is 0, y is 0. So there's no eigenvector. So this algebraically, we've just proven that this linear operator defined by A, it's a perfectly nice linear operator, but has no eigenvectors or eigenvalues in the reals. But suppose we let F be the complex numbers, and so A corresponds to a linear map from C2 to C2. So if A of xy is lambda xy, this means, just as we did before, lambda squared 1 plus x equals 0. But over the complex numbers, you can satisfy this equation with x different from 0 and lambda equal to plus or minus I. So there are two possible eigenvalues. If we choose lambda equal to I, then x is I times y. So xy is I y, or y times I1. So I1 is an eigenvector with eigenvalue I. Now let x equal minus I, x is minus IY. So I have the vector minus IY, y, or y times minus I1. So in this case, the spectrum of A is not empty. It has the vectors I and minus I in it. And these are eigenvectors. So it can be completely significant whether you're working over the real numbers or the complex numbers. And in this case, the same matrix, which represents a linear operator for R2 and a linear operator for C2, has no eigenvalues for over the reals, but it has two eigenvalues over the complexes. That's an interesting fact. Let's prove a few more things about eigenvectors and eigenvalues. Theorem 2, perhaps. So T from V to V and lambda 1 up to lambda K. This is a set of distinct eigenvalues. So suppose I have a set V1 up to Vk. These are eigenvectors. T of Vi is lambda sub I Vi for all I. So these are distinct, pairwise distinct eigenvalues, and the V's are the corresponding eigenvectors. Then this set of eigenvectors is linearly independent. Proof. So the proof will be by induction on K. K equals 1. We just have a set of one vector, V1, not 0. So it's automatically independent. The only time a scalar times V1 is the 0 vector is if the scalar is 0. What about K equals 2? That's the interesting case. So suppose we have C1 V1 plus C2 V2 equals 0. So T of 0 is 0. So that's T of C1 V1 plus C2 V2, because this is the 0 vector. This is a linear operator. This is C1 T of V1 plus C2 T of V2. But T of V1 is lambda 1, and T of V2 is lambda 2. So we have this equation, this equals 0. But also this equals 0. So if I multiply this equation by, I don't know, lambda 1, I get C1 lambda 1 V1 plus C2 lambda 1 V2 equals 0. If I subtract, these cancel, I get C2 lambda 2 minus lambda 1 V2 is 0. So this is a non-zero vector, it's an eigenvector, and this scalar times this is 0. So C2 times lambda 2 minus lambda 1 is 0. But the lambdas were distinct eigenvectors, eigenvalues. Lambda 1 is different from lambda 2, which means lambda 2 minus lambda 1 is different from 0. So if the product of two numbers is 0 and one is non-zero, then the other has to be 0. So C2 has to be equal to 0. So C1 V1 equals 0, and V1 is a non-zero vector. So C1 is 0. So that gives me a proof that if I have two eigenvalues and two eigenvectors, they're linearly independent. And the proof, the inductive step, is very similar. So assume the statement is true for whenever you have some K eigenvectors. And now we have K plus 1 eigenvalues. K plus 1 eigenvectors. And we want to show this set of K plus 1 eigenvectors is linearly independent. So suppose we can write 0 as a linear combination of these vectors, I must show that the CIs are equal to 0 for all I. Apply T to both sides of this. That's 0, T of 0 is 0, but because the operator is linear, this is C1 T of V1, CK T of VK, CK plus 1 T of VK plus 1. And because VI is an eigenvector with eigenvalue lambda I, this is C1 lambda 1 V1, CK lambda K VK, CK plus 1 lambda K plus 1, VK plus 1. I have this equation. I also have this equation. Let me multiply this by lambda sub K plus 1. So then I get C1 lambda K plus 1 V1, CK lambda K plus 1 VK, CK plus 1 lambda K plus 1 VK plus 1 equals 0. So I have these two equations, and these two terms are the same. So if I subtract, they cancel. And I get C1 lambda 1 minus lambda K plus 1 V1 up to CK lambda K minus lambda K plus 1 VK equals 0. But V1 up to VK are a set of eigenvectors for K distinct eigenvalues, and these vectors are linearly independent. That's the induction hypothesis. So of all these coefficients have to be 0. And the coefficient is of the form Ci lambda I minus lambda K plus 1 for I between 1 and K. And because the lambdas are distinct, this is the lambda I minus lambda K plus 1 is non-zero. So if this is 0, the only way that can happen is if C of the I is 0 for I going from 1 up to K, which means CK plus 1 VK plus 1 is 0. And this is a non-zero vector, so this scalar has to be non-zero. And we've proved all the scalars are 0. So this is the inductive step. All right. So there are many nice examples, but let me look at some of the homework. So exercise 1. We take the matrix A equal to 0, 1, 1, 0. And we want to find eigenvectors and eigenspaces for each eigenvalue. So lambda is an eigenvalue if and only if there's a vector xy different from 0, 0, where xy is lambda times xy. So if lambda is an eigenvalue, if there's a non-zero vector xy that satisfies this equation. What is on the left-hand side? 0, 1, 1, 0, xy, that's yx. And then we want that to equal lambda x, lambda y. So that's true if and only if y equals lambda x and x equals lambda y. So if x equals lambda y and y is lambda x, then x is equal to lambda times x, which is lambda squared x. So if x is different from 0, then lambda squared x equals x if and only if lambda is plus or minus 1. If lambda equals 1, you have to have x equal y. So we have the eigenvector xy. If y equals x, this is xx. This is x times the vector 1, 1. So suppose I let v1 equal the vector 1, 1. A of 1, 1, that's 0, 1, 1, 0 of 1, 1. That's 1, 1 again. So this is an eigenvector with eigenvalue 1. Should say, if x is 0, y is 0. If y is 0, x is 0. So in fact, you can't have x or y equal to 0. What about lambda equal minus 1? So a1, 1, which again is 1, 1. Oops, sorry. axy, which is, well, I don't even need to do that. Anybody did it? If lambda is minus 1 and there's an eigenvector, then y equals minus x, and x equals minus y. So xy is x minus x. That's x times the vector 1 minus 1. And if I let v2 be the vector 1 minus 1, a of 1 minus 1, that's 0, 1, 1, 0 applied to 1 minus 1. That's minus 1, 1, which is minus 1 minus 1. So minus 1 times minus 1. So a of the vector v2 is minus v2. So v2 is an eigenvector with eigenvalue minus 1. And it's the only one. So for the eigenspaces, E of 1 is just the one-dimensional space spanned by the vector 1, 1. And E of minus 1 is the one-dimensional space spanned by the vector minus 1, 1. So for this linear map, this is the vector 1, 1. That's an eigenvector with eigenvalue 1. 1 minus 1. That's the vector v2. That's an eigenvector with eigenvalue minus 1. So this vector is stretched. Sorry, yeah. This vector is fixed, and this vector is just reflected through the origin. Yeah, that's problem 1. Maybe I went through it too quickly. So if there are any questions about any of this, I'm happy to go through it again.
So Professor, what was the eigenvector for number 1 again?
1, 1.
1, 1, and then the...
And for the eigenvalue minus 1, the eigenvector was 1 minus 1.
Okay, thank you for clarifying.
Let's look at exercise 2. So we have the matrix minus 3, 0, 5, 2. So A applied to the vector xy is minus 3, 0, 5, 2 applied to xy. This is minus 3x plus 5y, 2y. And we want to know for what values of lambda is this equal to lambda of xy. In other words, when can you solve the vector equation minus 3x plus 5y, 2y equals lambda x, lambda y. So for that to happen, minus 3x plus 5y equals lambda x, and 2y equals lambda y. So of course, if y is 0, if y is not 0, then lambda has to equal 2. And so we have the equation minus 3x plus 5y equals lambda x, which is 2x. So that's the same as saying that three x plus 2x, 5x equals 5y, x equals y. So if you take lambda equal 2, say the vector xy, if x equals y, this is just xx. This is x times the vector 1, 1. So if I take v1 to be the vector 1, 1, this should be an eigenvector with eigenvalue 2. So A applied to 1, 1, minus 3, 0, 5, 2, applied to 1, 1. This is minus 3 plus 5, 2. That's 2, 2. That's 2 times 1, 1. So lambda is an eigenvalue, and v1, 1 comma 1 or 1, 1 is an eigenvector for lambda. That's if y is different from 0. Let's see what happens if in the other case. If y equals 0, then minus 3x plus 0, which is minus 3x, equals lambda x. So if y is 0 and x is not 0, then lambda has to be minus 3. And xy is just x 0, or x times 1, 0. So if you let v2 be the vector 1, 0, I claim this is an eigenvector with eigenvalue minus 3. And in fact, A applied to the vector 1, 0 is minus 3, 0, or minus 3 times the vector 1, 0. So lambda 2, my second eigenvalue is negative 3, and 1, 0 is an eigenvector for that. Right. Let me do one more, maybe problem 5, because that involves a 3-dimensional matrix. So A is the matrix 1, 0, 0, 2, 3, 0, 0, 0, 7. And if I apply that to the vector x, y, z, I get x plus 2y, 3y, 7z. And suppose that's going to be equal to lambda times x, y, z. There's lambda x, lambda y, lambda z. So the only way that can happen is if x plus 2y equals lambda x, 3y equals lambda y, 7z is equal to lambda z. So let's look at separate cases. Suppose, say, case 1, if z is not 0, 7z equals lambda z implies lambda must equal 7. If lambda equals 7 from the second equation, 3y equals 7y, it means y has to be 0. And if y is 0, x equal to 7x means x has to be 0. So the only vector I get with eigenvalue 7 is of the form 0, 0, z, or z times 0, 0, 1. So lambda equals 7 is an eigenvector, is an eigenvalue. The eigenvector 0, 0, 1. Right? If z is different from 0, lambda must equal 7, and that implies that y and x have to be 0. So we just have this vector. What about case 2? Suppose that y is different from 0. Then 3y equals lambda y means lambda has to equal 3. If we have 7z equal 3z, then z is 0. If we have x plus 2y equals 3x, that means 2y equals 2x. That means x has to equal y. So it looks like if y is different from 0, x has to equal y. And an eigenvector would have to be of the form y, y, 0, x equals, or y times 1, 1, 0. Let's check. What does A apply to the vector 1, 1, 0? That's 1, 2, 0, 0, 3, 0, 0, 0, 7. Apply to 1, 1, 0. That's equal to 3, 3, 0. That's 3 times 1, 1, 0. So 1, 1, 0 really is an eigenvector with eigenvalue 3. So in the first case, z was non-zero. In the second case, y was non-zero. So the only thing left are the cases when y and z both equal 0. In that case, these equations just say 0 equals 0, and this says x equals lambda x, so lambda has to equal 1. So I can take x 0, 0, or x times 1, 0, 0. And if I take the vector v3 to be 1, 0, 0, A of v3, if you do the calculation, is v3. So v3, 1, 0, 0, is an eigenvector with eigenvalue 1. That is the proof of it all. Okay, any questions about this? All right. I'll do some more on Wednesday, some more of the homework problems, but I want to just review a little bit of high school algebra. Suppose we want to solve ax plus by equals 0, cx plus dy equals 0. So we always have the zero solution, x equal y equals 0. And the question is, when is there also a non-zero solution? Well, if we multiply the first equation by d and the second equation by b and subtract, you get ADX minus BCX is 0, or AD minus BC times X is 0. If AD minus BC is 0, then this implies that X must equal 0. And if X is 0, sorry, if AD minus BC is different from 0, then the only way this is 0 is X is 0. And if X is 0, then BY equals DY equals 0. You can't have both B and D equal to 0. So B equal D equals 0 means AD minus BC is 0, which is not the case, right? So at least one of B and D is non-zero, so Y equals 0. So if AD minus BC is 0, the only solution of these two linear equations in two unknowns is 0, 0. If AD minus BC does equal 0, then X can be anything. And what can you say about Y? So let's see. I want to show that if AD minus BC is 0, there's a non-trivial solution. So why is that? Well, I can do it in a painful way. So if B and D are both 0, then I can let X equal 0 and Y equal 1. That's a solution, because you get 0 plus 0 equals 0. So otherwise, at least one of B or D is non-zero. So suppose that D is not 0. If D is not 0, Y is minus CX over D. Right? CX plus D equals 0. Solve for Y. Y is minus CX over D. So AX plus BY is AX plus B times minus CX over D, which is, I put this over a common denominator, AD minus BC over D times X. And that's equal 0 for all X. Say X equal 1. So if I let X equal 1 and Y equal minus C over D, I get solutions of this equation, non-zero solution. So this is just my little bit of whatever it is, high school algebra. So this is useful to know. ax plus by equals 0, cx plus dy equals 0, if and only if AD minus BC, has a non-trivial solution if and only if AD minus BC is 0. That's the same as saying that if I take the vector xy and multiply it by the matrix ABCD, that's equal to 0 if and only if AD minus B equals 0. And if we let A be the matrix ABCD, what we call the determinant of A is AD minus BC. That has to equal 0. So if you have two equations and two unknowns, there's a non-trivial solution if and only if the determinant is 0. So that's just a useful fact. So let's go back to eigenvalues. Just looking at dimension 2. So the dimension of V equals 2. So V is like this two-dimensional vector space over the field F. And suppose A is the matrix A, B, C, D. So with the operator T from F2 to F2, defined as usual by T of xy, is the vector A times xy. That's A, B, C, D times xy. That's AX plus BY, CX plus DY. And T of xy is an eigenvector with eigenvalue lambda, if and only if I can solve this equation with x and y not both 0. But T of xy is AX plus BY, CX plus DY. And that's supposed to equal lambda x, lambda y, which is the same as solving these two equations, AX plus BY equals lambda y, CX plus DY equals lambda x equals lambda y. Or if I put everything on the left-hand side, A, or everything on the right-hand side, it's the same thing. Lambda minus AX minus BY equals 0, and minus CX plus lambda minus DY equals 0. So for this two-dimensional vector space F2 and the linear operator defined by the matrix ABCD, xy is an eigenvector with eigenvalue lambda if and only if xy solves these two equations and two unknowns for some value of lambda. And this has a non-trivial solution for lambda if and only if the determinant of this is non-zero. The determinant is this times this, lambda minus A, lambda minus D, minus B times minus C, which is BC, if and only if that equals 0. Or if I multiply this through, this says lambda squared minus A plus D lambda plus AD minus BC equals 0. So lambda is an eigenvalue if and only if these equations have a non-zero solution. That means these equations have a non-zero solution. That means the determinant of this, which is this quadratic equation in lambda, has a non-zero solution. But there's a formula for solving a quadratic equation. So if I just write down everything that I just said, lambda is an eigenvalue for the matrix A, B, C, D, if and only if lambda is a root of the quadratic equation, and we know what the root of a quadratic equation is if and only if lambda is minus b plus or minus the square root of b squared minus 4 AC over 2 times 1, which is a plus d plus or minus the square root. This is a squared plus 2ad plus d squared minus 4ad plus 4bc. 2 minus 4 is minus 2. So this is a plus d plus or minus the square root of a squared minus 2ad plus d squared plus 4bc over 2, which is, let me just bring out the 1/2. 1/2 a plus d plus or minus the square root of a minus d squared plus 4bc. So given a matrix A, B, C, D, there are only two possible eigenvalues. Over the reals, there are two eigenvalues. If this quantity is positive, there's one eigenvalue if this quantity is 0, and there is no eigenvalue if this quantity is negative. Over the complex numbers, there's one eigenvalue if this is 0, and two eigenvalues if this is not 0. So in the first example I looked at, I had the matrix A, which was 7 minus 4, 5 minus 2. So lambda is 1/2 a plus d, 7 minus 2 is 5, plus or minus the square root of a minus d, 7 minus minus 2 is 9 squared, plus 4 bc is 4 times 5 times minus 4. So that's 1/2 5 plus or minus the square root of 81 minus 80 plus or minus 1. So that's 1/2 5 plus or minus 1. If I take plus 1, 5 plus 1 is 6 over 2 is 3. If I take minus 1, 5 minus 1 is 4 over 2 is 2. So the only eigenvalues for this linear map, the only possible eigenvalues are 3 and 2, which is just what we saw in the initial problem. So let's do a few more problems because these are important computational techniques. Suppose I take the matrix A equals 3, 1, 2, 4. So again, the only possible, if I have A equals A, B, C, D, the only possible eigenvalues are the roots of the quadratic equation lambda squared minus A plus D lambda plus AD minus BC equals 0. So for this equation, A is 3 and B is 4. So we get lambda squared minus 7 lambda plus AD 12 minus BC 2, 12 minus 2 is 10, equals 0. So what are the roots of this? Well, this I can actually factor because this is equal to lambda minus 2, lambda minus 5. So the only possible eigenvalues are 2 and 5. So let's find the eigenvectors. If I take A, apply to the vector xy, 3, 1, 2, 4, apply to xy, that's 3x plus 2y, x plus 4y. That's going to equal 2xy, or 2x, 2y, if and only if 3x plus 2y equals 2x, x plus 4y equals 2y, which is the same as saying x plus 2y equals 0. In fact, I get the same equation from both. So if and only if x is minus 2y. So we get the vector xy is minus 2yy, or y times minus 2, 1. So this must be an eigenvector with eigenvalue 2. Let's just check. 3, 2, 1, 4 times minus 2, 1 is minus 6 plus 2 is minus 4. Minus 2 plus 4 is 2. This is 2 times minus 2, 1. So this vector is just stretched by a factor of 2. What about the second eigenvalue, 5? So for lambda equal 5, I get the equations 3x plus 2y equal 5x, x plus 4y equals 5y. This says that I bring this over here. 2y equals 2x, or x equals y. This says x equals y. So my only possible vector is xx, or x times 1, 1. And if I take the matrix 3, 2, 1, 4, and multiply that times the vector 1, 1, I get 5, 5, which is 5 times 1, 1. So 1, 1 is an eigenvector with eigenvalue 5. Questions about this? All right, let me do one last example, and then that'll be enough for today. Suppose I take the matrix A equal to 1, 2, 2, 3. So to say that A of xy is lambda times xy is the same as saying that 1, 2, 2, 3 of xy, which is x plus 2y, 2x plus 3y equals lambda x, lambda y. So x plus 2y equals lambda x, 2x plus 3y equals lambda y. Again, this is the same as saying that lambda minus 1x minus 2y equals 0, and lambda minus 2x minus 3y equals 0. In any case, what are the possible values of lambda? So this is A, B, C, D. The quadratic equation is lambda squared minus A plus D. A plus D is 4 plus B squared plus AD minus BC. This is my equation. Lambda squared minus A plus D lambda plus AD minus BC equals 0. A plus D is 4. AD is 3. BC is, AD is 3. BC is 4. 3 minus 4 is minus 1. So my equation is lambda squared minus 4 lambda minus 1 is 0. So lambda is B minus B, that's plus 4, plus or minus the square root of B squared minus 4AC, minus 4 times minus 1 over 2. That's 4 plus or minus the square root of 20 over 2. That's equal to 2 plus or minus 4 times 5, square root of 4 is 2, 2 plus or minus the square root of 5. So in this case, I have two eigenvalues, 2 plus root 5 and 2 minus root 5. So let me see if I can find eigenvectors for each of those eigenvalues.
Professor,
Yeah,
when you set the two equations to 0, the second one, when you factored out, why do you factor out x instead of y? Where you set the
here
equation
and
to
here?
0? Yeah, the second one, yes.
I didn't factor anything out exactly, but this is 2x plus 3y equals lambda y. Oh, I just wrote it down wrong also. Thank you. So if I bring everything from the left side to the right side, I get minus 2x plus lambda minus 3 y equals 0. Or maybe I should have just simply said 2y equals lambda minus 1 times x. So y is lambda minus 1 over 2 times x. And the second equation says 2x is lambda minus 3 times y. It should turn out to be the same thing. X is equal to lambda minus 3 over 2 times y. So let's just see what happens. If lambda, if I take the plus sign, is 2 plus the square root of 5, then lambda minus 1 is 1 plus the square root of 5. And divide that by 2 is 1 plus root 5 over 2. So y is going to be 1 plus root 5 over 2 times x. So if I let, for example, x equal 1, then y is 1 plus root 5 over 2. And my vector xy is 1 plus root 5 over 2. Let's just do an experiment. If I take lambda minus 3, that's minus 1 plus root 5. So lambda minus 3 over 2 is minus 1 plus root 5 over 2. So x is minus 1 plus root 5 over 2 times y, where y is 2 over minus 1 plus root 5 times x. If I multiply top and bottom by 1 plus root 5, I get 4 in the denominator, I get exactly the same thing, 1 plus root 5 over 2 times x. So this is an eigenvector with eigenvalue 2 plus root 5. And if I let lambda be 2 minus root 5, I'll get another eigenvector for that eigenvalue. Yeah, that's what it is. So the spectrum of this matrix A consists of 2 plus root 5, 2 minus root 5. Those are the eigenvalues for this linear operator. That is the state of the art. Any questions? So I'll talk more about eigenvalues and eigenvectors on Wednesday. And then we have a break for a week and also start to say something about inner product spaces. Someone's asking about the next exam. So we come back from break on the 22nd, the 25th of April. So I think the exam will probably be on May 4th.
You mean the second one?
Sorry?
The second one, right?
The second exam on Wednesday, May 4th.
May 4th. Is there going to be a review before then?
Sorry?
Is there going to be a review?
Yeah, the review will be on Monday, May 2nd.
Okay, thank you.
And the final exam is on the final exam schedule, and I believe the final exam is, let me just write this down. So exam 2 is Monday, sorry, this is the review, which is Monday, May 2nd. Exam 2 will be Wednesday, May 4th. And the final exam is 2 weeks later, Wednesday, May 18th.
All right. So where can we get more practice on the eigenvalue?
Sorry?
Where can we get more practice on the one that we just finished right now?
What do you mean by practice? You mean more? There are a lot of examples worked out in my notes. So working through the examples in the notes.
The one you put on the blackboard?
Yes.
Oh,
Yeah.
all right.
Now I'm just following my notes. They're better, I think, than the textbook.
The last one you put down is on the change of the basis. So is there anything new?
Yeah, there's something on eigenvalues.
All right, I'm gonna check it.
Yeah.
Thank you. Do you have office hour today?
Sorry?
Do you have office hour today?
Tonight, I think it's 7 o'clock tonight. I'll send out an email.
Okay, thank you.
Okay, any other questions? If not, then looks like a nice day. Hope everyone can get to enjoy it a little bit. And I'll be back on Wednesday. But we'll have I have office hours this week. There's some office hours, Monday, Tuesday, Wednesday, and Thursday. And I'll send out an email right away with the hours. Okay. All right, take care, everyone.
Take it easy, Professor. Thank you.
Thank you.